think I had to get out of the full screen, so it's sometimes an accident. So here's a bit of review for some of you and new material for some others. This is the idea of how of a single level ordered logic. So I'm going to use this example because I thought it was an interesting question. It's to do with a statement that said labor government makes life better. That was included in the British election studies in 2001. And it was a 5-point response scale. I collapsed the responses in what you could call people who disagreed, people who were neutral towards the statement, and people who were not. And I gave them numbers, actually I gave them numbers 0, 1, and 2, but you could also give them numbers 1, 2, and 3. The numbers themselves are not important. What is important is the random order between the numbers, because I'm assuming this is an ordinal scale, that there is a property here, namely believing that labor makes life better, and you can have more or less of that property, and if you have less of it, you will tend to disagree with the statement, and if you have more, you will tend to agree with the statement. And in fact, that's the very idea that I'm going to exploit, this idea of this underlying property. And that's what is going to be used to then model the probability of giving one or the other response. So here is something that we did before with logic. We say, well, underlying this y, there exists a latent variable, y star, that captures the attitude with infinite precision. We just don't know how, we don't measure that. We actually just think of that as some latent constant. And then we say, well, if the latent attitude exceeds this certain threshold, then the individual picks a particular response. And thresholds are also known as cut points, and then the relationship between y and y star and the cut points we can indicate in the following graph. So I already made a distributional assumption here, a normal assumption or a logistic assumption, but that is actually not so critical yet. When we have this underlying latent variable y star, and we have there two cut points, I'm calling them kappa 1 and kappa 2. And this kappa 1 is a cut point that demarcates response 1 from the response 2, and kappa 2 is a cut point that demarcates response 2 from response 3. And the way you can think about it is, if your latent attitude falls short of kappa 1, that is, you really are not inclined to think that labor makes your life better, then you will be giving the response, I disagree with the statement. Now, if you at least exceed this kappa 1, then you sort of have at least some inclination to say that labor makes life better, but you're not wildly enthusiastic about labor. You fall short of kappa 2, then you will say, well, I'm neutral towards the statement. And if your latent attitude exceeds kappa 2, that is, you're actually fairly enthusiastic about labor making your life better, then you will say, okay, I agree with the statement. That's the idea. So we go from below kappa 1, 2, kappa 1, and kappa 2, 2, and beyond kappa 3, we get the response 3. Actually, I'm going to set up the model a little bit different from what I just told you. I'm going to actually talk about the cumulative responses. And so actually I will ask first, well, what is the probability of giving a response greater than 1? That is, what is the probability of being at least neutral to the statement? And that is, of course, then equal to y star exceeding kappa 1. And then I'll ask, okay, what is the probability of the Q of the response exceeding 2? That is really being 3 in this case. And that I will then say means y star exceeds kappa. So that's the setup. Now we're going to say a little bit more about this y star because we may have some ideas about why people might in their attitudes believe labor makes their life better. And those ideas we can capture in predictors. So, I mean, the ones that I'm going to look at in this example are 3. I again have this identified labor, sort of to pick up on the idea that if you identify with labor, you probably believe labor makes your life better. Then I have this left-right distance again to sort of pick up on the issue dimension or the ideological dimension of politics. And there the idea is, of course, that if you were further away from labor, your latent attitude will be more negative towards labor, which then means you're probably more likely to say, to disagree with the statement. And then the third one that I've included is the emotional reactions toward the economy. And I've taken there a battery of 4 positive emotions and 4 negative emotions. And I've taken the sum of the positive emotions minus the sum of the negative emotions. So that ranges from -4 to +4. -4 if you really don't have any positive feelings about the economy and only negative feelings. And +4 if you only have positive feelings about the economy and no negative feelings. And then we have at the end here an error term epsilon, because there is no pretense that we can fully account for this underlying attitude with just those 3 predictors. There's probably other things. Maybe someone is hungover, and you could ask them a question about anything making their life better. Does your wife make your life better? And they probably would disagree with it. Well, you don't want to necessarily create a variable to pick that up, but you can sort of assume it flows into this error. So now we need to link this to what we actually observe. That's important because we don't actually observe this y star. We only observe these 3 responses. And I'm going to do that in the cumulative fashion that I just talked about. So I'm going to define a probability by I parentheses m. And that is just shorthand to say probability that an individual I's response is greater than some category M. So I can say, well, the probability that Y is a response greater than 1. The probability that I is a response greater than 2, and so on. And what we now do is then say, okay, well, going back to this picture, if you want to give a response greater than 1, then your y star has to exceed kappa 1. So, more generally, if your response has to exceed m, some category, then your y star should exceed the threshold associated with that category. And then we just substitute this equation for y star. Then we rearrange terms a little bit, so we get then epsilon greater than kappa m minus all of these effects of the predictor. And then if epsilon is normally distributed, or actually if epsilon follows a symmetrical distribution, then we could take advantage of the following property, that probability of epsilon being greater than something is the same as the probability of epsilon being less or equal to the negative of that something. And if you take the negative of this term to the right of the right-hand of the equality sign, inequality sign, we get this expression here. And that is a cumulative probability, and so we can say that is then some cumulative distribution function f evaluated at beta 1 epsilon I plus all the way to beta pxp I minus capital. And then the choice is, well, what do you pick? And there are basically two choices, but I prefer to work with the logistic distribution. So we can either pick the standard logistic distribution function to create an ordered logic model, or we can pick the standard normal distribution to create an ordered model. Again, if you pick the standard logistic distribution for this epsilon, you are fixing the mean of the epsilon to 0. That's what you would do in a hierarchical linear model as well. But different from a hierarchical linear model, you're also fixing the variance of this epsilon. There is no sigma squared that you're going to be estimating, because that sigma squared is fixed to the variance of the standard logistic distribution, which happens to be pi squared over 3. Now, these cumulative probabilities, the probability of scoring more than 1 or scoring more than 2, they're not all that interesting in a sense, because we're really usually interested more in the probability of scoring in a particular category. The only reason I set it up this way is actually that it leads to a fairly simple expression at the end. But we can always backtrack the probability of actually scoring exactly in categories of them. So the probability exactly of saying that you disagree with the statement. And that is then just simply equal to this expression here, the predicted probability at the previous cumulative predicted probability minus the current predicted probability. So if you want to know what is the probability of scoring 2, what you do is the probability scoring greater than 2, and compare that to the probability scoring greater than 1. The probability of scoring greater than 1 is this whole area to the left of capital 1 on the curve. The probability of scoring greater than 2 is this last area to the right of capital 2. If you subtract that area from the first area, you're left with exactly the area that you want. And there's just one little detail to add there. Say that M is your first category, then what is pi I m minus 1? It doesn't exist, but actually the way we solve that is to say, well, if I want to know what's the probability of being in category 1, we say, well, it's equal to the probability of being in a category greater than 1. That probability, if you subtract it from 1, gives you this probability. And that's effectively our probability. So here is then the estimates. So labor identifiers, they tend to think that labor makes their life better because we impose a positive coefficient. Ideological distance, the more of it, the more people seem to disagree, be inclined to disagree one's economic emotions tend to be more favorable, people tend to be more in agreement with the statement. That much you can tell right from looking at these estimates. But you cannot really say exactly what the magnitude of the effective labor identification is, or ideological distance, or emotions. To get to that, we would have to actually then really get to odds ratios or predicted probabilities. Now, one little point that I need to emphasize before we go there is that when you look carefully at this equation here, you will notice that there is no constant term in that equation. And there's a reason for that. The constant term is not identified. There's no way to estimate it with the data, because what is the data? The data essentially, what we eventually have is a set of probabilities, a set of proportions rather. The proportion of people that fall in category 1, the proportion of people that fall in category 2, the proportion of people that fall in category 3. And those proportions we can use as estimates of our probabilities. Probability of being in category 1, 2, or 3. Well, we know that these proportions add up to 1. And that means that there are really only 2 unique proportions. There are only 2 unique probabilities. And that means we can only identify 2 cut points. If we want to also try to identify a constant in addition to that, we're trying to demand too much from the data. So we drop the constant, we keep the cut points. So let's do interpretation via predicted probabilities first. So here I have the effect of positive, negative economic emotions. I have actually computed that here for people who do not identify with the Labour Party and who are at a median ideological distance from Labour, which is 1. And you see that the -4 here is people who only have negative feelings towards the economy, only positive feelings towards the economy. You see here the trajectory of disagreement, the probability of disagreeing. We see here the trajectory of agreeing with the idea that Labour makes life better, and this is the trajectory of actually saying I'm neutral towards the statement. And again, when I would write a paper with an ordered logic model, this is the kind of thing that I would show, because it tells basically what is going on in the data.
Do you think it would be okay if I'm only interested in one of the values of the dependent variable? So let's say we disagree, and if I only plot that line as opposed to plot both 3 lines.
It's okay, but if you're only really interested in one category, then why not collapse the whole thing and just make it into a dichotomy and then proceed from that perspective? And the reason I'm saying that is not just because it's a simpler thing, but it also allows you to avoid one tricky issue that I sort of have brushed aside here, but will mention it. In this logic model, or probe model, doesn't matter, they both make this assumption. You'll notice that the effect of beta, the effect of predictors, the betas, are not in any way, shape, or form subscripted by the response categories. This is known as the parallel regression assumption. And this is a major assumption in ordinal logic problem models. And it's an assumption that is a bit heroic, because you have to say, well, the effect of being a labor identifier is the same when you look at your inclination to say, I agree with the statement, as your inclination to say, I'm neutral towards the statement. Maybe be the case, may not be the case. And that's sort of the assumption you buy into here. Now, there are ways around it, but if you want to generalize those to multi-level analysis, they become very complicated. And you don't have that problem in the simple logic setup. So that's why I would say just collapse it and you solve this problem as well.
When displaying the results, if you have three categories, what is your take on the ternary plots? Like these triangle plots with the predicted probabilities. It's also in ELECDEM clarified sometimes.
Yeah,
if there are three categories.
Yeah.
So whether that would be acceptable as a...
I think so. Well, it has Gary King's stamp of approval, so then I think that actually it's probably acceptable. So, no, I mean, again, with these things, I think it's important to graphically depict the results because it makes it much easier to tell the story. But how you do that, I think, is in large part a matter of preference, because then you can say, well, if I'm comfortable with those plots and I find it much easier to talk about them, then that's what you want to show. And if you're more comfortable with this kind of setup, then that's what you want to show here. So I think that's a matter of taste. But again, I think what is important is just as with logic, never just report a table of coefficients. Don't just do this and say, well, here you have it, because it doesn't say all that much. You could just broadly say labor identification increases the likelihood of agreement, ideological distance decreases, but that doesn't really tell a lot. And then I think you either want to tabulate some scenarios, but I actually think it's much better to just graphically display what's going on. Now, the other way to interpret this is again to go to this concept of odds ratios. But odds ratios in ordered logic models take on a slightly different guise than they do in logic models, because in logic models it's sort of clear what the logic is. It's the log of the probability of scoring 1 over probability of scoring 0. Here what they tend to do is turn it into a cumulative odds ratio, and a cumulative odds, when they say the cumulative odds is the probability of scoring greater than category M over the probability of scoring in category M or picking a smaller category. So for example, the probability of being neutral towards the statement or agreeing with the statement versus the probability of disagreeing with the statement. If we did M and on. And we can then accordingly talk about cumulative logic, which is an idea that I will introduce here because we're going to use it for the multi-level extension. That's just the natural logarithm of this whole thing. And of course, if you take the natural logarithm of the right-hand side, you're just left with the linear function beta 1x1 plus beta 2x2, etc., minus the couple alpha. Now, again, what you could do is to say, well, imagine we hold all of these predictors constant, but I'm going to increase this x1 by 1 unit. Then we could say, what happens to the cumulative odds. We take the cumulative odds when we didn't change that variable. We take the cumulative odds when we change that variable to 1 point higher, and we compare the two odds, and it turns out that that produces a factor change that is again really fairly straightforward. It's equal to e raised to the power whatever the coefficient is that is associated with the predictor we have changed by 1 unit. And the interpretation is maybe even more tricky than it is in normal logic, because what are we talking about? We're talking about a factor change in this thing. It's really, when you want to interpret it, the factor change in the odds of picking a higher category over a lower category. But as you'll notice here, this factor change doesn't actually depend on which category you're considering. So the factor change is the same when I substitute 1 for small m here, or when I substitute 2 for small m here. That's again, by the way, a function of that parallel regression assumption I mentioned. But it's sort of hard to wrap your brain around it. So if I increase ideological distance by 1 point, the effect on the odds doesn't depend on which category I substitute here. So if I say, what is the probability of scoring greater than 1 versus less or equal to 1? That's saying, what is the probability of saying neutral or agree versus disagree? That's affected in the same way as when I say, what's the odds of scoring greater than 2? That is, what is the odds of saying I agree with the statement versus I feel neutral or I disagree with the statement. That's hard to wrap your brain around. But that's a fundamental attribute of this odds ratio under parallel regression. So here are the odds ratios, and we see actually that pretty substantial effect of labor identification. It's sort of trivial, but the odds of picking a higher category tending to agree more with a statement as opposed to the lower category increase by a factor 3 when you compare non-identifiers to identifiers. The ideological distance has an effect, but this factor change is relatively close to 1. This is not a huge effect. Actually, the economic emotions seem to have a bigger factor change, which suggests that they might actually move the response probabilities a little bit more. Now, does all of this make some sense? Because now I'm going to turn this into a multi-level model. And here is why I might want to do this. Often the distribution of the responses varies over context. And to accommodate that, we can actually add a random intercept. Of course, if we also expect the effect of a predictor to vary across contexts, we can also add random slopes. But here's just an example of this variation in the responses. This is the constituency Dundee West, and this is the constituency Beaconsfield. And in Dundee West, the overwhelming majority of the respondents, not many of them, but the overwhelming response of the respondents seems to be, yeah, labor actually made my life better. In Beaconsfield, there actually seems to be much more inclination to say, well, neutral or actually disagree with that statement. Those are very different response distributions. Now, if we go back to this model here, and we were to strip away all of the predictors in this model, so basically, if everything said is done, is we have basically just here the probability of scoring greater than m is epsilon being greater than kappa m. Then the way the kappas would be chosen is actually to adjust them to the proportion of people that score in category 1, the proportion of score in category 2, the proportion of score in category 3. But in a single level ordered logit model, those proportions would be the aggregate proportions. So aggregating over all of the constituencies, what proportion of individuals in the UK said they disagreed, said they were neutral, said they were agreed. And that is what drives these cut points. But if you have this kind of situation, you'll notice that in these individual districts, the response distributions look very different. And so you would expect the cut points in Dundee West and Beaconsfield to be selected very differently based on the response distribution. And that feature is actually something that we would like to capture in a multi-level analysis. Does that make sense? And that is what I'm going to start out with. I'm actually not going to initially add any predictor value variables. What I'm going to do is actually just include a kappa and then a random component. But more generally, if we want to formulate a random intersect model, then of course we could add predictors with fixed effects. The only thing that is now different from the model that I presented before, aside from the fact that we have another subscript here, is the fact that we have this delta 0j added. You can think of this last term, this delta 0j minus kappa m, as a context-adjusted cut point. And this is one example where I played with this. So the global cut points I set here at -1 and 0.5, and then I said we have deltas of -1, 0, and 1. So adding that into the logit, we have delta 0j minus kappa m, and that leads to very different response probabilities. So if you think delta 0 is -1, you have a very high probability of scoring 1. If delta 0 is 1, you have a very high probability of scoring 3. That's the kind of thing we want to be picking up. So how do you estimate this in Stata? And again, this is one of the really nice things about GLAM, is that it actually allows you to estimate this model. There is nothing else in Stata that allows you to estimate a multi-level ordered logit model. But it works. And the syntax is relatively the same, except we change the link function. The link function is now an O-logit link function, which stands for ordered logit. And the second line here is just, again, to get empirical base predictions, which I will use in a moment to show you a little bit how actually the cut points vary across the distance. So here we go back to the example. Does labor make life better? And there are no predictors in this model. The only thing that is in there is the cut points and this delta 0. And this delta 0 ends up having a fairly small value in terms of its variance. The variance of the delta 0 is 0.04. So you might wonder, well, is that really enough to say we really need to do this? So what I actually end up doing is estimating an ordered logic model as well, just with the cut points. And then I did a likelihood ratio test. Again, as I showed you yesterday, to pull that off in Stata, you have to force it. So you have to add option force. And you get a chi-square with 1 degree of freedom, because there's only one variance component, of 4.45, and a half p-value that is 0.018. And therefore, you can reject the null hypothesis that there is no variation in these cut points in the population. So I took that as evidence that we really should specify a random intercept model. And here are the empirical based residuals. So these are my estimates of the delta zeros obtained using this command here. And you see there is actually quite a bit of variation. You see the cut points are negative 1.11 and 0.44. And you would add to those cut points these empirical based residuals, then you see that there's some variation. And that there's some districts where you have delta zero that is quite negative, and some districts where it's quite positive. If you go back to this story, that would suggest in these very negative districts more of an inclination to low response, and in these more positive districts to big high response. Now we could add random intercepts and slopes. If we do it just for one predictor, say the first one, we would add this component, delta 0j plus delta 1j, x1ij. And we could then more generally do everything random, but I would not actually recommend that, because these models have typically a much harder time converging than things like hierarchical linear models. The estimation, by the way, is the same as what we discussed last week. So based on yesterday, so basically adaptive quadrature. So here is then a bit about interpretation, and this follows exactly the pattern that I described for the logic model, because really nothing changes. We can use odds ratios for the interpretation. We can use predicted probabilities for the interpretation. When we do predicted probabilities, we can use marginal predicted probabilities, or we can use conditional predicted probabilities. When we do the odds ratio interpretation, we start out again with the logit, and usually what we end up doing is a fixed effects interpretation, where we take the expectation of the logit, which then means basically these terms delta 0j, delta 1j, x1ij drop out. And we're left just with the fixed portion and the threshold. And then what we typically do is say, well, let's take one predictor and increase it by 1 unit while holding everything else constant. And that means if, say, we change the predictor xp by 1 unit, then the change in the logit is equal to beta p, the coefficient that's associated with that predictor, and the odds ratio, which is just the expected, the e raised to the power of the logit within the e raised to the power beta. And you see here that the results that we get from doing that in terms of does labor make life better are actually virtually indistinguishable from what we had in the original logic. There's a reason for Because it turns out once I include these predictors, the variance in the cut points, so the delta 0 J variance, basically goes to 0. That can happen. Because variation in the cut points can come about also by individual level variation. So if you take that into consideration, you might find that there's really not much variation left in the cut points. And so actually, by the time you include these predictors, you could just as well estimate an ordered logic model without worrying about the multi-level structure too much. Now, in terms of the predicted probabilities, we can calculate marginal probabilities and we can calculate conditional probabilities. And what I will do is I will actually show you how to do this because I didn't write down the syntax. So, let me see. Here. This is a random intercept model that I'm going to be estimating. Life bet is the dependent variable. Lap ID is identification with later. Left-right distance is left-right distance. And ECHEMO is the emotional reactions to the economy. So, here we go. Won't take much long. It only takes about 4 iterations of the analytic function for the Newton graphs. Again, 2088 level 1 observations, 127 level 2 units. Condition number, again, we like that to be lower rather than higher. This is fine. You just don't want it to be in the thousands. Then you really start to worry that you have identification issues. Then here are the results, and as I already said, once you include these individual level predictors, the variance in the cut points seems to have disappeared. This is 0. 1.5 raised to times 10 raised to the power negative 13 is not interesting. So now I want to obtain the cumulative predicted probabilities, the cumulative marginal predicted probabilities, and here is the syntax. It's again GLA pred, then you give it a name. It's again mu, because we want to predict the probability, marginal because we want it to be a marginal predicted probability, but now we have to tell GLM which one we want to calculate. We want to calculate above 0, we want to calculate above 1, because I coded my variable 0 like 2 rather than 1, 2, 3. And then that has run. Then here I convert these into predicted probabilities for the actual categories that I'm interested in. So just the way I described it. And then here is the graph that gives you then the pattern. And this graph is indistinguishable from the one that I showed you before. That is basically the same pattern, actually the same values on the vertical axis, so nothing all that interesting. What we can do as well, of course, is to actually compute the conditional predicted probability. So we could say, well, I want to have the conditional probabilities taking into consideration the value of the delta 0. Except it's not that interesting here because the delta zeros are so small, because the variance is so small, you basically are adding a bunch of zeros. That's not all that interesting. You could do it. In which case, you would issue the following syntax. The same as what I had before, I just dropped the term marginal. So here we have that, and then we convert them to probabilities proper, and then I just want to show them for 2 districts, Dundee West and Beaconsfield. So here. Created the dummy apparently. Still doesn't like that. And then here you see the patterns. And now, of course, again, these patterns, they just take into consideration also the fact that this is Dundee West, this is Beaconsfield. They also take into consideration the empirical range on the predicted, which in this case, among people who are not labor identifiers, apparently there's quite a bit of pessimism among the Dundee West people. They are emotionally not too happy about the economy. People in Beaconsfield seem to be much happier. So that's why you get short little lines on the left and much longer lines on the right. That seems to capture that aspect. But again, this would sort of be a redundant picture because we've already discovered that there really is no variation in the cut points, so we might as well approximate every single district with the same set of lines. That's what I have shown. And that is your ordered multi-level logic model. So it is basically the ordered logic model, and if you just do a random intercept version of the model, which is really all I've done here, it is just a matter of saying the cut points can shift from one level to unit and that then is going to potentially affect the distribution of the responses and therefore also the predicted probabilities. That's the bottom line. Doesn't work out in this example, but there are certainly other examples where it does work out. And again, the way you calculate the predicted probabilities is not fundamentally different than what you have in the logit, and it's also not fundamentally different when you start looking at odds ratios. That's also very similar, except in these ordered models, you always look at cumulative odds as opposed to odds of one category